Folks, this is tutorial number 10, which belongs to a playlist called Kinematics using the 3D Experience platform. Uh, what I have here is a very simple problem. I have a wheel which is supposed to roll along this path. Okay. Now, I'm assuming that the center velocity or the speed of this center point as it rolls is 10 millimeters per second. So based on elementary dynamics, if you take the velocity, that center velocity, and divide it by the radius, you will get the constant angular velocity of the rolling motion. So it's going to be 4.77 RPM. Okay. Now, keep in mind that this thing, as it spins, it also rolls about the vertical axis or rotates about the vertical axis. This is why towards the end, this 4.77 RPM is the rolling speed or the magnitude of the speed towards the end of this spline. Okay, so I try to make it as straight as possible because when it gets to this point, when it gets to that point, there is no rotation about the vertical axis, and obviously there is no tilting rotation, and therefore this formula is actually the angular velocity, or let me see now, this formula is the spinning velocity of that wheel on that horizontal, on that almost flat path. Now, it is true that even here, the angular velocity is the same thing, but the spinning velocity is the same thing. But there are other angular velocities, which is rotation about the vertical axis, which contributes to that. So I'm not interested in this. Okay, I'm only interested in the spinning motion on that horizontal or that straight line segment. Now, uh, the strategy that I'm going to follow, this is not the best one. This is not the only one. What I'm going to do is I'm going to create a spline here, and I'm going to translate that spline up by a certain amount, and that amount happens to be the radius of the circle. Okay, and what happens is that I'm going to have a point curve join. The center of the circle is going to be traveling along that path, and there is a rolling motion, which is going to be a roll curve joint, which is going to be down uh, the spline below it. Okay. Now, just to see that this is actually rotating, I made a little indentation here, so you can see that actually this is rolling. Uh, Although this is not any one of these specific chapters coming out of the book, but it is essentially related to the topics covered in this book. Okay. So let's go ahead and do that. I'm going to make the base first. So insert a 3D part. I'm going to make the base just a box essentially. So double click on this. And on the horizontal plane, I will sketch something with roughly those dimensions. So let's see now. Something like that. Let me put some dimensions here. So this is 300 millimeters. Close enough. That's good. And this one is roughly 100 millimeter. Okay, 120. These numbers don't matter. It's just that I wanted to have roughly same scale that you see there in the slide. So exit, and I'm gonna pad this thing by okay, I have to be in part design if I'm gonna pad. Let me go to part design. Okay, part design. So I'm gonna pad this thing. What is it? Essentials. Okay, pad this. I'll make it maybe 7 millimeters, something like that. Okay. Now, on that surface, on that top surface, I'm going to draw a spline. Now, to draw a spline, I cannot be in part design. I have to go to generative shape design, or I can go to the stripped down version of generative shape design, which is called generative wireframe and surface, or generative shape design. That's entirely up to you. So let me go to generative shape design. On that face, I will sketch. Okay. So I'm going to draw a spline here, but I'll make sure that kind of towards the end, it's almost flat. So let's see now. The spline is right here. So let's say that we start there. A bit more. So over here, it's almost a flat line. Almost. Let me make it a little bit, yeah, flatter. Almost straight line. Good. Exit. Now I want to translate this thing up by 20 millimeters, which is the radius of that circle. So let's go ahead and where is the translate under probably the transform offset. Let's see now if we can find translate here. Is there a translate? No. Translate right there. Okay, I want to translate. Translate. It was this icon. This thing in the vertical direction Z by 20 millimeters. There we are. Okay, so that takes care of this. Now there is a couple of things I want to do here because this wheel is supposed to roll on that bottom curve. Uh, it must be tangent to that, and this my strategy for making the tangent to it is to first to create a plane, a normal to that bottom curve at that location. See that? This bottom curve, I make a plane normal to that, and then another plane which is perpendicular to that normal plane, which means that that second plane is going to be actually tangent to that curve. So, as I said, there are different ways of doing this thing, but this is how I'm going to do that. If you go to this part, go back here, let's find the planes. So essentials, here's a plane, and the method of using the plane is going to be normal to a curve. Normal plane, normal to a curve. And the curve is right here, the bottom one, and the point is right there. Notice that it did create a plane there. Now, this plane is normal to that. It's not tangent to this, but what I'm going to do is create another plane which will actually be tangent to that, okay? So let's see now, another plane. And the method that I'm going to use, for example, there are different ways of doing it. For example, we can say uh, angle normal to a plane. So the rotation axis, well, the rotation axis is that vertical axis, but if I don't have any, I can always go create that line or create that rotation axis, basically create a line between 2 points, between this point and this point. The sole purpose of that is to be able to use that as rotation. I don't know, offset, that's okay. So that's fine. Uh, so this is good preview. So it's right there. And then we say, okay. So we created the rotation axis, and then reference is going to be this plane that we created. And we're going to make it 90 degrees. Or if you click on that icon, it makes it actually 90 degrees right there. So the original plane was normal to this curve. And the only reason that I did it is because I wanted to create something that is normal to that original plane, which automatically makes that tangent to this curve. Okay, so that takes care of this, and that's the explanation behind these things that you see here. Now, let's go ahead all the way to the top and insert our wheel. So right click, insert a 3D part. Okay, let's go make it on any plane. For example, on the, I don't know, on that YZ plane, I will sketch. That's totally, so sorry, sketch. Just a circle of radius uh, 20 millimeter. Okay, and so that I can see this thing is rotating later on, I'm going to make a little feature here, exit, and then I pad it. Now remember, I'm in generative shape design, so to pad it, I'm going to go back to part. Yep, and then I'm going to pad it by I don't know, maybe 10. Let's see how it looks like. Yeah, so that's going to be the wheel, and then we say okay. All right. Now I do need a point at the center of this. Remember, because we're going to making a point curve joint later on. So what I'm going to do is I'm going to say, okay, make a point. And the way I'm going to make that point is center of a circle. And this is the circle that I'm going to select, and it's going to make the point right there. Okay. Now we are pretty much done. So let's go ahead to the top level assembly design, and we're going to start putting constraints there. So assembly, let's fix this base first of all. So under the connection, under engineering connection, click on the fix, and it's going to be the plate basically. It's fixed now. Now I want to take this point and put it right there. So we go to engineering connections. Okay, let's do that. Click on it. Oops. Just click on it. And I'm going to use coincident between this point and that point. And I want this to be turned around and placed on that plane. So let's see now. Another coincidence between this plane and that plane that I drew to make sure that it is normal to the original one right there. And then we say okay. We don't want any contact. So notice what happened is that, first of all, the center of that disk is at that point. And the way of the construction work is that I made sure that this plane is tangent to that. And I made that coincident with this. Oh, excuse me. Wow. Okay, let's move on. Now these constraints that are created, this last one is just was created because of the constraints that I put in there. I don't need it. I'm going to delete this. Okay. All right. Good. We are pretty much done. So let's go ahead to. Uh, oh, before I do that, let me show you something. We are in assembly design. I can create those point curve and roll curve joints right now, or I can do it later. So let me do that right now. So let me go to engineering connection one more time and select the point curve joint right there. See the point curve joint? And this is the template that I'm going to use, the point and the curve. It says select the point. So there's the point. Select the curve, and there's the curve. All right. And then I also want to do a roll curve joint. So let me say okay here. Notice that the point curve joint has been created. Now I'm going to click on the engineering correction again. Choose the roll curve joints. Scroll down so you get roll curve joint. So there's one curve, and there's the other curve, and it's a new connection. Say okay, and okay, and no to contact. Okay, so these are created, point curve and roll curve. Okay, so let's go ahead and uh, first of all, let me do a quick save here. Good. So now let's go to the application which does the mechanism. So mechanical systems design. Okay, here we are, mechanical systems design. Let's make the mechanism representation, and say okay. Good. If you click on the manager, you see that there's a fixed plate, there is the point curve joint, length driven, and there is the roll curve joint. Now, automatically, it was given commands here, and I'm going to uncheck these. See that? Because the motion of that point curve joint, will dictate the rolling action. So notice that these two were put automatically for me. I took it off. So the only thing that I have is the point curve joint is actually, uh, distance driven. Say, okay, good. Let's check it. If you click on the mechanism player, and you drag this thing, this point should stay on that curve, and this should roll. So let's try it. See that? I put that feature over there so you can see that it's actually rolling. Now, I mean, obviously, if you want to go further than that, then you have to change the range here, but that's really not the intention right now. So let me put it back where it is, and we say, okay. So as far as this problem is concerned, basically we have finished it, except that there's no physics into it. So let's go and put the physics into that. So in order to do that, you have to go to mechanical systems experience, say okay, so that kinematic simulation is created right there. First thing I'm going to do is to specify the speed of that point. So to do that, I use the excitation. See that law excitation? Select that command, that length driven command, remember, for the point curve joint. Click on f of x, and right now it says 0. It's going to go in the right direction, plus. You can take that 0 out if you want, but I'll just leave it the way it is. Plus. You can backspace so that that 0 millimeter is gone. But anyway, so it's plus 10 mm underscore s, 10 millimeter per second, times time. Select the time, left double click on this. So now this says that that point has a constant speed of 10 millimeters per second. We say okay. Say okay. So excitation has been created there. Now let me also find a probe, and the probe is uh, angular velocity, about the vector of angular velocity. Okay. Now the problem is that the vector of angular velocity here only is going to be constant later on. You see that constant spinning motion over there, over here, because this thing also rotates about the vertical axis and spins. So the vector is not going to be only the spinning contribution. So let me go and select the probe here. And I'm going to select the same point. Same point. Say OK. All right. We now go create a kinematic simulation. So create the excitation one that we created, send that to the right side. Probe that we created, send that to the right side. Right now, it's 10 seconds. So basically, it's going to travel a distance of 100 millimeters. So let me make this thing bigger. So let me make it maybe to, I don't know, maybe 35. Okay. All right, and then make this thing 0.1, because otherwise we very jagged, and we say okay. Now we're gonna compute it right there. We created our scenario. We're gonna compute. Okay, 35 was probably a little bit more than what I wanted. So let's if we don't want to see that, okay, let's go ahead and change that thing to 30. How about that? I'll make that thing 30, 30. Actually 29. How about that? Try it again. Okay, good, good, good. Now, well, first of all, you can play the cartoon if you want. So play animation. You can make it play over and over and over. If I can make it forward and backward, this is just a cartoon. Well, right now it's a cartoon, but there's physics in it. Okay, so close that. Now let's plot the stuff. So I'm going to click on the view scenario results. I don't want everything. What I do want is angular velocity, angular vector of angular velocity, the magnitude of angular velocity. Now it's not going to be constant, but towards the end, it better give me 4.77, something along that line. So I selected this and I click on the plot, okay? So you can see that obviously it's not constant, but down here, where this line segment was straight, look at the value that I get, 4.77696, etc. So it is only the spinning motion over there, which is the angular velocity of the wheel about its spinning axis. All right, folks, so it is correct. Good. Good luck.